Good morning, afternoon, and evening, everyone. Welcome to episode 63 of HYSKY Monthly. Richard, since you're the co-host, if I miss somebody in the waiting room, could you please let them in? That'd be great. Thank you so much. We are so excited to have you all here this morning. We have a really special presentation from Southwest Research Institute here in Texas. And so we're just going to jump in and do a couple of announcements, and then we will hear from our amazing presenters. I will ask that you all hold your questions until the end. You're welcome to put your questions in the chat, but let's answer them after the presentation. So, as you all know, I'm Danielle McLean. I'm the founder and CEO of HYSKY Society, and this is HYSKY Monthly. HYSKY Monthly is sponsored by Piasecki Aircraft Corporation, SoCalGas, Vertical Flight Society, Thurman Company. And if you're interested in sponsoring one of these webinars, just send me an email, d@hysky.net. These do go on YouTube, they are recorded, and they get hundreds of views as well. So today's presentation is going to be an introduction to SwRI's hydrogen energy research areas. Happy late Valentine's Day. I hope you had a weekend full of love or work, love for work, as mine was. So just a little about HYSKY Society. We're a 501c3 whose mission is to advance hydrogen aviation. We come from the eVTOL sector, but we love all things hydrogen. We're based in Houston, Texas. We're building a global community that includes you all. And we bring that community together in person annually at our Flying High event. I'm going to talk a little bit about advanced air mobility because it gives a good idea of why hydrogen is so important. But we work with anybody that's using hydrogen as a fuel. So that could be fixed wing, could be aerospace, dirigibles, anything that defies gravity with hydrogen, that's part of our ecosystem. But if you're using a battery powered eVTOL, yes, you could fly over traffic. That's good. But you can only fly about 60 to 100 miles, and that's okay. And so, speaking from a Texas perspective, yes, you could fly from Houston to San Antonio. I'm using San Antonio because that's where SwRI is located. But you wouldn't be able to do it without stopping to charge, and that's bad. And we see Mr. Musk is just irritated waiting for the Beta aircraft to charge. No offense to Beta. I love the Beta aircraft and everything they're doing. They are working on some really cool charging technology. It just happened to be the only image I could find of a actual eVTOL being charged. So you're still gonna have to wait and recharge. So hydrogen can extend the range a lot. Hydrogen can extend the range to well over 300 miles. This opens up city to city travel, life-saving flights, which average about 300 miles, regional air mobility, and emergency search and rescue. And for those of us Houstonians, you can think floods and hurricanes. There's a lot of opportunity for hydrogen. And this is an old slide, an oldie but goodie, but it really demonstrates if you were, and this could be for fixed wing aircraft too, but this is for an eVTOL. So from point A to point B, it's 300 miles. If you were doing that with just batteries, you're going to stop and recharge 2 times at least. If you were to do that same flight with hydrogen, you could go all the way there with that one fueling of hydrogen. And, just to kind of give you an idea that this is actually happening, Mike Hirschberg, who I believe is on the call today, wrote an amazing article for Forbes. Hydrogen is a game changer for vertical flight. And there's the Joby aircraft. We had them last month presenting on their 500 plus mile hydrogen eVTOL flight. China's just did a liquid hydrogen eVTOL aircraft. They've just done their first flight, their first test flight. Again, this is the Joby 500. It ended up being like 560 miles. You can go back and watch that. Unither Bioelectronics and Robinson are partnering to build hydrogen powered helicopters to deliver organs, like I was mentioning, life-saving flights. Um, and then this is kind of just an overview of the current state of hydrogen in aviation. This slide is actually a year old. I need to update it because I need to add Robinson and some other folks to this, but this just kind of gives you an idea of how many aircraft, how many companies are building and developing hydrogen aircraft. And yes, you may have seen in the news last week that Airbus is delaying their hydrogen program, but they're still very much focused on hydrogen. They're just doing SAF first. And that makes sense because, we talk about SAF being kind of a precursor to hydrogen. So make no mistake, Airbus still knows hydrogen is the only way to zero carbon flight, but they're just delaying that project a little bit, about a decade. So they're still in the game. So hopefully your next logical question is, what about infrastructure? Because that's exactly what HYSKY asked. Well, the Department of Energy funded 7 hydrogen hubs in the United States to scale clean hydrogen production. Each of those 7 hubs was awarded about $1 billion. And Houston is part of one of those largest hubs, and that's called the High Velocity Hub. I'm bringing up Houston because HYSKY is based in Houston, but we're working with all of the hubs, but we're especially interested in the one here in Houston. So these are all 7 of the hubs. We have the Pacific Northwest Hub, the California Hydrogen Hub, the Heartland Hydrogen Hub, the Midwest Hydrogen Hub, Appalachian Hydrogen Hub, and the Mid-Atlantic Hydrogen Hub. All of these hubs also have nicknames. For example, the California one is called Arches, ARCHEES. The Gulf Coast Hydrogen Hub in Houston is called High Velocity. So if you hear somebody say the Houston Hub or the Gulf Coast Hub or the High Velocity Hub, they're talking about the same thing. And that goes for all of them. They all have nicknames. I don't know, us scientists, we love our acronyms. So it's just as much a thing in energy as it is in aviation. So these are the 7 hubs. Like I said, each of these were awarded about $1 billion each, give or take. And so HYSKY's role in all of this is we bridge the gap between hydrogen and aviation. So on the left, again, HYSKY is located in Houston, so we're very focused on this Gulf Coast hydrogen hub, but we bridge the gap between all of these companies that are developing hydrogen powered aircraft. That is our role. We are the bridge. This is just a quick video to demonstrate, and don't worry, there's no sound, but just to demonstrate, again, I'm in Houston, so I selfishly made this to demonstrate what I would like to do with hydrogen-powered eVTOLs. See if we can get it to play. No recharging. You can go straight there without having to stop and recharge. So how can you get involved? You can attend HYSKY monthly, which you are if you're here live. If you're watching this on YouTube, you can register in the link in the description. We just had Joby present their 500+ mile hydrogen flight. That was an amazing presentation. You can watch that on YouTube. Around the corner, and I think it's 33 days to be exact, we're hosting the Hydrogen Hub Summit. So those 7 hubs that I talked about and showed you, we'll have a speaker from each one of those hubs. Definitely go register for that. It's only $30. It's a half-day virtual event. And let me just put the link in the chat that you are definitely going to want to register for that, because even if you're here for the aviation piece of it, if you don't have the hydrogen, then, what are you going to do? You need to be involved with these hubs. So I encourage you. This is brand new. You haven't missed a lot. They're just now getting their first phase of funding. So attend on March 19th so you can hear from those hubs and directly get involved with them. Another way to get involved is you can partner with us on our in-person annual summit, Flying High, which is going to be in Houston in December of 2025. We are very excited, so stay tuned for more news on that. But definitely, definitely, definitely get your tickets to the Hydrogen Hub Summit. I don't know why my slide won't advance. There we go. This is just more about the hub. About the Hub Summit, the H2 Hub Summit. It's March 19th on Zoom. Tickets are $30. That's where you can register. I think we even have it set as our homepage right now, so you can just go to hysky.org. You can also sponsor. It's tax deductible, and sponsorships start at $250. The last Hydrogen Hub Summit had over 200 attendees. We're expecting over 300 this year. So you can sponsor for $250 and advertise to all 300 guests for very cheap. You can download the sponsorship brochure here, and I will also put that link in the chat as well. These are some of our sponsors and supporting organizations. Hi Axiom, a Doosan company. Very exciting. Check them out. AIAA, hopefully most of you are very familiar with AIAA, if not members. Heaven Drones, they're a hydrogen-powered drone company. Earth and Water Law, I believe Paul Sarahan is on this call. They do basically environmental law. Morton and Company, they do insurance for the aviation space. Hondo Economic Development also includes the South Texas Regional Airport. I hope I said that right. But they're doing some very exciting things around hydrogen as well. So shout out to Scene, who is hopefully on this call. Also, Leibold, our branding sponsorship of the year, also our sponsor of the year in 2024. They're doing some very exciting things with liquid hydrogen storage. Vertical Flight Society, I've already mentioned Mike Hirschberg. Many of you are probably aware of Vertical Flight Society, but they are all things vertical flight, including eVTOLs. And then Two Veridi is hydrogen anywhere, anytime. So we've got some excellent sponsors. Thank you all so much for supporting our event. Hopefully we'll be adding Southwest Research Institute to that list soon. Another thing you can learn is if you're already an engineer, especially an aerospace engineer, and you want to learn more about, say, how you can design a hydrogen-powered eVTOL or a fixed-wing hydrogen aircraft, or you want to learn more about advancing hydrogen at the airports, or you want to learn about hydrogen storage. Again, this is for existing engineers, unless you're very diligent and studious self-taught engineer. It's a very technical course that we partnered with AIAA on. It's 20 hours, 10 lectures, and you can take that course. We did it live at the end of last year, but you can get the course on demand. So I will post that in the chat. Oh, hi, Angela. You're here and doing links. Thank you so much. I love when I see that as a surprise. All right, time for a group picture. So if this is your first time, at this time, we ask that everybody turn on their cameras, and we're going to take some group pictures, and then we're going to tag you on LinkedIn if you have a LinkedIn. So I'm going to stop sharing my screen and give everybody a minute to turn on their cameras. And Angela, if you could also take some group pictures, I find sometimes different people get different views. Okay, this is a great one. Okay, everybody say cheese and hold it because there's a delay. That's one. Saving that. Okay, then we're going to do another one. Everybody say cheese. I see there's a lot of people that still don't have their cameras on, or maybe you turn them off. It does take a minute. Hi, Santh. I haven't seen you in a while. Your face just popped up. Good to see you. Hi, Gaber. Also good to see you. Cameras on if you can. By the way, Santh, you won a ticket to Flying High last week here in Houston. I mean, not last week, but last month. So congratulations on that. I don't know if you saw that. And we're gonna do another picture. Say cheese. Hopefully you're getting some of these, Angela. And let's do one more. Perfect. All right, back to sharing. Okay, awesome. So today's speakers. I'm so excited. We have two speakers, Denis M. Long, a good friend. Denis Long is a senior program manager in the Powertrain Engineering Division at Southwest Research Institute, otherwise known as SwRI, is a leader in powertrain, battery, and propulsion technologies across automotive, aerospace, and marine sectors. With over 30 years of experience, he has driven innovation in drivetrain systems, hybrid vehicles, and energy solutions. He began his career at Mason and Hanger, Silas Mason Company, managing high explosive machining facilities before joining SwRI in 1995 to specialize in transmission testing and hybrid development. Rising to lead the drivetrain engineering section, he later founded Global Powertrain Engineering, expanding drivetrain testing and development before selling his shares in 2009. After a successful tenure in the healthcare sector and leading EV and hybrid drivetrain testing and at Intertech, he returned to SwRI in 2020 to spearhead major commercial and government programs shaping the future propulsion and energy systems. And before we welcome Mr. Long, let me read you Dr. Richard Fu's bio. Dr. Richard Fu, a research engineer at Southwest Research Institute, specializes in hydrogen technologies, fuel cells, and electrolyzer system testing within the fuel cell research and innovation section. He leads validation testing for major automotive clients, including durability, life cycle, altitude, and hardware in the loop tests. Dr. Fu also advances high temperature polymer electrolyte membranes and water electrolysis technologies and plays a key role in H2HD Refuel, a consortium focused on hydrogen refueling stations. With a PhD from the University of Connecticut, his expertise spans clean energy, neutron radiographic analysis, and computational fluid dynamics modeling, driving innovation in sustainable energy solutions. And with that, I would like to pass it over to our distinguished speakers, and I'll handle the letting people in from the waiting room right now. So Dennis and Richard, over to you.
All right, Danielle, thank you. Appreciate that, the introductions and the opportunity to allow us to present to you guys today. The way we're going to do this is I'm going to do a quick overview of Southwest Research for the people who are not familiar with Southwest. And then
Dennis,
I'm going to pass it to...
I apologize to interrupt. Do you think you could sit in front of Richard's computer so that we could see you on camera?
Am I not on camera?
Well, since you're using Richard's mic, it's pulling up him as the speaker. You see what I mean?
I apologize for that. We thought we had that worked out.
No worries. That was my fault. I should have caught that in our in our pre-testing in our tech.
Okay. I'm not Richard Fu. I'm Denis Long. Right here. There.
There we go.
You can see me now. Sorry about that. Full disclosure, we quit using Zoom years ago. We're on Teams, so we're not exactly experts on Zoom, but nevertheless, the way we're going to do this presentation is we're going to split it up. Richard's going to talk about the hydrogen things we're doing in this area at Southwest. I'm going to give an overview of Southwest Research. Also, some of the items that Richard is going to present, he's not necessarily the one that's the expert in that area, because we have a lot of different areas that we work with hydrogen, and we will not be able to cover all of those today. But I'm gonna go ahead and move on. For those of you who are not familiar with Southwest Research, as Danielle mentioned, we are located in San Antonio, Texas, our main headquarters. You can see from this photograph, we have a rather large footprint. We're about 15 minutes from downtown San Antonio, believe it or not. But we are one of the largest independent research companies in the United States. Let's see. We were founded back in 1947, so over 75 years. We too are a nonprofit, just same as Danielle's group, pushing 3,200 employees. You can see all the stats there. This place was founded by the son of an oil man that came from Oklahoma. Oddly enough, the last name is Slick. But it just evolved over the years into where we are now, and I'll touch on some of those things here in a minute. We get our revenue, and we are a nonprofit, 501c. We get our revenue from contracts, either federal or commercial contracts. And there's various ways we could contract. I'll talk about that in a minute. Sometimes they come individually, and we also run several consortia. And the last slide I'm going to present will give you an overview of some of those consortia. and I'll get into that when we get there. We're pushing close to $1 billion in revenue at the end of FY24. I would say over the next couple of years, we probably hit the $1 billion mark. We deal with a broad technology base, as you will see in a minute. Very capital intensive. We have a lot of equipment, a lot of facilities, a lot of under roof space for testing and development. And one of the unique things we do is we have internal research programs where if engineers or anybody comes up with an idea that seems to be something worth pursuing, something that could go to market, we present to our executive board, they fund it. And as you can see in 2024, we did about $11 million of that and 119 different projects. When you contract with us, we have a lot of different ways to contract. One of the top bullet there, the flexible IP policy is unique in that if we're working with a company and we're working on something that is novel and new that gets developed, that IP is theirs. I mean, obviously we identify any IP we have going in so everybody is aware of anything like that. But if it's new, the client usually owns it. There's different ways to contract with us, fixed firm price, cost plus, time and material. The fixed firm price contracts, honestly, are probably a little more pricey in a sense because we're taking all of the risk. We are taking all of the risk, but there's cost plus and time and material too for when you get into development projects, things like that. The project progression that you see there at the bottom, we have the technical discussions, we finalize scope, we formalize what we're going to do. The last bullet there says contract negotiations. That actually happens a lot of times in parallel. We have the NDAs in place and all this stuff, obviously, before we do any type of technical discussions. This is a map of where we are, San Antonio, like I said, down there in central Texas, not far from, up the street in Austin, but we have places across the United States. We support different military bases. In Ann Arbor, we have some automotive work there. We do some controls work up there, and over in the UK, we have a design group that works over in the United Kingdom, and then some facilities in China as well. So we're spread out across the world, but mostly in the United States. The tagline you see at the top, from deep sea to deep space, is truly, it's real. We work on submarines. I say we collectively at Southwest Research. We work on submarines that go to the lowest depths of the ocean, to putting stuff on different satellites that are being launched. I think there's probably 2 or 3 in space right now that are active. I could get the name of them if anybody's interested. We have automotive divisions. We have chemistry and materials out at Southwest on our grounds. We get involved with defense and security. You guys could read the list. It's a wide range of different areas that we get involved with. Much like the way Danielle described HYSKY, is kind of the way Southwest is set up. We bridge the gap between universities and industry. We do not make a product. We get involved with the basic research across. You can see the bottom, the applied research, product development. We do pre-production work, but we turn it over to industry when you start to get into the production side of things. So we also bridge that gap, like Danielle was mentioning. This is my last slide. This is the consortia. I hope it's not an eye test for you guys, but we get involved with many different companies that come together. They have a common problem. Instead of everybody trying to develop something individually, they get together and say, okay, we have these common problems. The consortium members vote on what type of research and development we're going to do. We do the work. We manage the consortia. So we're very adept at doing that type of work. One of the examples I could put in the lower, I could draw you to is the lower right-hand corner of this is the AFEB. It's a fluids group for electrified vehicles. A vehicle could be an aircraft or a land-based vehicle, either one. But you'll see that we have 26 members in it and many different research tasks. And some of these go on for quite some time. The one right above it's a electric diesel engine one, hybrid electric diesel one, and it's been running since 1991. So I think this is where I hand it over to you, Richard. Sorry for going through that somewhat fast, but we have a lot of material to cover. So Richard's going to be Richard again.
All right. Okay. Can everybody hear me all right? Okay. I hope so. All right. Thank you so much, Dennis. Good morning, everyone in the US, and good evening to your audience in Europe and in Asia. My name is Richard Fu, and today I will be introducing SwRI's hydrogen energy research areas and activities. Hydrogen has the highest specific energy at 120 megajoules per kilogram, and it burns clean and with only water as a byproduct. And therefore, because of the high energy density per weight, it is an attractive fuel for aviation. I think that is why you are tuned into this webinar. But hydrogen is also very flammable and very difficult to store and handle. To this day, people still associate hydrogen with the Hindenburg accident that happened 88 years ago in 1937. And it has really forever, altered our perception of hydrogen. And therefore, it is the engineers' responsibility to design and build safe vehicles and infrastructure, especially in aviation. At SwRI, we offer the R&D and testing services to perform these due diligence to develop vehicles and aircraft equipment. Okay. So as you heard from Dennis, we have over 3,000 researchers and engineers working on wide-ranging facets of hydrogen energy from production to end consumption. So I cannot really talk all in 30 minutes or so, but I would like to introduce a few select areas of our activities today. So here's the list. The first is about our fuel cell R&D and testing services. Next, I will talk about our H2HD refuel consortium. And lastly, I will touch upon the safety standard tests. And if I do have time, I would like to touch upon the H2I's development also. And should you be interested in any other areas of our activities, please contact me or Dennis, and I'll be more than happy to send you the information. Okay, so moving on to the fuel cell system testing experience and capabilities. So SwRI has been working with hydrogen for several decades. And here I'm picking up some of the more recent activities in fuel cells since 2021 or so. And I'll be talking about some of these projects. The first one is about our internal research, which Denis mentioned. It was a benchmarking and controller development research of Toyota Mirai. In 2021, we began this test with a phase 1 research to understand the state-of-the-art FC vehicle at the time. It was the Gen 2 Mirai. We hooked it up a bunch of instruments to investigate how the stack performed on the various drive cycles, and to look at how the balance of plant, such as the compressor, HRB, and coolant pumps supported the stack operation. The findings from the benchmarking study were that the Mirai stack was very transient and provided more than 50% of the power. Stack performance dropped off and vehicle derated at high load and high temperatures. air bypass valve led to efficiency losses. So, that was a potential for optimization. Controller was sensor-based rather than model-based, and humidity control was passive. So therefore, active model-based controls could improve stack performance. So that's what we exactly did in the phase 2. We built our own model based on controller, model-based controller, and compared it with that of the original ECU output. We were able to demonstrate that our controller was within 7% of MirrorEye's ECU and closely emulating it. And here you see the picture of the fuel cell stack and the DC to DC converter. And lastly, in phase 3, and this is our ongoing research, is to replace the ECU with our own, with the full controller in place. We demonstrated that we can independently control the balance of plant and the vehicle itself. We are currently working on improving the efficiency of the vehicle. And lastly, I'm showing you the actual setup of the test in our lab. And with this, we can perform various hardware in the loop tests to evaluate, different components such as compressors, heat exchangers, and so on. So, should you have any component that you would like to test, we will be able to do so with this setup. Next, we'll move on, and I'd like to mention some of our fuel cell system testing capabilities that may be relevant to aviation and aerospace industries. The first one is thermal chamber testing to examine the effects of extreme environmental conditions, in this case temperatures, on the performance. The fuel cell system is blurred out to protect the client design and information in the picture. With this setup, we can perform cold start tests or thermal soaking to simulate long-term storage conditions, as well as temperature stepping, temperature, humidity, cycling, and so on. And another environmental test capability we would like to add is altitude testing. So please stay tuned for that. The next test that I am sharing with you is a compound angle tilted fuel cell system test. So can your stack perform when it is not upright? Will the FC be able to effectively avoid flooding when it's on its side, or will the compressor move enough air at an odd angle? So these are some of the questions that this test can answer. The test was originally developed for off-highway vehicles, but I believe it is equally or probably more relevant for aviation fuel cell systems. And in this picture, in life cycle or durability tests, we stress not only the fuel cell stacks, but also the balance of plant to evaluate the system performance over time. In protecting your CapEx, very expensive CapEx investment, you want to make sure the system will operate properly for thousands of hours under steady state and dynamic drive conditions, drive cycle conditions. We can examine the system performance for 2,000 or 3,000 hours or whatever you define. And we will look at the performance degradation over this time to calculate the estimated end of life. And lastly, in addition to fuel cell for mobility, we can test large stationary fuel cell systems. This, the one pictured right here was a 500 kilowatt power generation system for data center backup. We assemble for our customer, but we have the capacity to test up to several megawatts if needed. And now transition into single cell level testing and short stack tests. So fuel cell MEAs or membrane electrode assemblies are at the heart of the fuel cell system. So as you develop or test the MEA, it is important to really understand and know that it can withstand for tens of thousands of hours with accelerated stress tests. We can perform these AST tests with load cycles such as the ones defined by million-mile fuel cell truck consortium or customized temperature and humidity cycles. The setup can be used for contamination tests if you're interested in running on reformed hydrogen sources as well. And once a single cell performance checks out, we can perform in a short stack to validate in multi-cell configurations. Again, we will be able to run various drive cycles and environmental conditions as you wish to prescribe. And now I'd like to switch gears to talk about our material research and development effort into high temperature polymer electrolyte membranes. And this one is one of the topics that we are considering for the upcoming fuel cell consortium, which is in the planning currently. But I wanted to touch upon it because I feel it is important for the aviation fuel cell community as well. So up to now, I have talked about testing of low temperature PEM fuel cell systems, but for fuel cell systems for heavy duty vehicles or aerial vehicles, we need systems in several hundred kilowatts range. And the consensus of many of the heavy duty OEMs and likely also from the aviation industry is that there are a number of issues that the fuel cell systems need to overcome before full commercialization is possible. So one of the issues is the waste heat rejection. And as you can see in the back of the truck over here, that these big radiators are usually mounted on, and it becomes very bulky, and it actually limit the power density of the vehicle. So a lot of previously discussed problems today stem from the use of traditional perfluorosulfonic acid membranes like Nafion and Nafion in PEM fuel cells. And Nafions have chemical and structural limitations and can only operate up to about 80 degrees Celsius, and therefore they are called low temperature PEM. And because it can only operate at low temperatures, it must rely on very expensive catalysts, such as platinum, to facilitate the oxygen reduction reaction. Even then, the activation over potential is still high, and therefore the power density is limited. And because it uses platinum, it is not tolerant of contaminants like carbon monoxide, and therefore very pure hydrogen must be supplied. And because of the temperature limitation, waste heat rejection is difficult, and large and bulky radiators are required. Nafion proton conductivity is heavily dependent on its water content. So because the conductivity is affected by the water uptake, it cannot operate under dry conditions, and therefore it requires a humidifier and complex system to make sure that the membrane is wet. And because the membrane uptakes water, it cannot operate or be stored at below 0 degree Celsius. And therefore purging and antifreeze heating and are required, and making the system inefficient and even more complex. And finally, these membranes emit PFAS during manufacturing, and that can linger in the environment for a long term. So it poses health risks to us. So many of these issues can be potentially solved by transitioning to higher temperature PEM FCs. And many of the non-fluorinated membranes are easier to synthesize, and therefore the cost can be lower. It operates around temperatures between 120 to 200 degrees Celsius. Therefore, the reactants are typically single phase, and so that you do not have flooding conditions that impedes oxygen transport. Because it operates at a high temperature, it has the potential to use precious group metals that are inexpensive and less susceptible to CO poisoning. Because it operates at a higher temperature, again, heat rejection is easier and requires smaller radiators and simpler balance of plant. The reaction kinetics is facile at high temperature too, so higher power density is possible, at least in theory. And the stack can be smaller because the conductivity is not water dependent. It can operate in dry conditions, and thus no humidifier is needed, and making the balance of plant lighter and simpler also. So even though I have listed all the potential benefits, however, the reality is not that simple. The HT-PEM still has many limitations today, and many of the current high temperature PEMs are polybenzene imidazole based membranes with phosphoric acid as the ion conductor. So therefore, the proton conductivity is limited, and the performance is still not on par with that of Nafion today. The phosphoric acid can gradually leach over time and leads to conductivity degradation, making the MEA short-lived. In general, the phos acid has low conductivity at low temperatures, below 21 degrees. Due to the phase change, so that the cold start operation can be one of the challenges. To solve these challenges of the high temperature, PEM SwRI is jointly working on this issue with the University of Connecticut on a new material innovation, which we call ordered metal organic framework composite membrane. And while I'm not able to disclose too much about this today, due to low TLL, it involves the fabrication of and alignment of ionically conductive MOF in an ordered manner. The proton conduction can be water independent, thus it can operate at high temperatures and low humidity. The substrate is very stable mechanically at wide-ranging temperatures and has the potential to exhibit very low crossover as well. So suitable for both fuel cells and electrolyzers. And these are some of the characteristics requirements for the high temperature PEM, and similar to what's set by the DOE. So we plan to fabricate the samples in the near future to validate its feasibility. And while the material is still in the development, it has attracted some interest, and we would like to build a consortium with this topic as one of the core programs. So should you be interested, please reach out to me again, and I'll be happy to discuss more. And so far, I have introduced you to some of the fuel cell R&D and testing services offered at SwRI. Many of these will not be possible without the early investment into the liquid hydrogen infrastructure on campus. The liquid hydrogen tank was installed and commissioned in 2024. It is a photon storage that is capable of providing hydrogen at 350 bar with a flow rate of up to 150 kilograms per hour. The hydrogen is currently piped to 3 of our buildings and supporting hydrogen activities in 21 cells. And while it was a much needed infrastructure to support the growth of the hydrogen testing activities, it was not without many challenges also. So we learned them really the hard way. So that is a perfect segue to my second topic for this webinar. So I would like to move on to H2HD Refuel Consortium. So whether hydrogen fuel cell trucks or hydrogen internal combustion engine trucks, or even airplanes. None of them would be possible without proper hydrogen infrastructure in place. So, however, as of today, there are only a handful of stations in the US that are capable of filling at the rate of 300 grams per second. And according to the J2601-5 standards. And to my knowledge, First Element Fuel and Nikola have taken the initiatives to do so, to build the heavy duty refueling stations. But my information is limited to the US, but I believe the situations are similar in Europe or Asia. So, and also I'm hearing that the several initiatives to develop hydrogen infrastructure at the airports and to support the aviation applications, but I am not aware of any in operation as of today. So there are many reasons for the lack of or the lag in the refueling station build out. And the primary reasons are obvious ones, very high CapEx involved and unproven reliability of the equipment, and also unsettled and ongoing technology development of the refueling station designs, and the logistical and supply chain issues. Leveraging on the liquid hydrogen facility that was already invested, SwRI is taking the initiative in bridging the gaps in the technologies with our latest consortium, again, which we call H2HD refuel. It's an acronym, it's a long acronym I'm not going to read right now, but the idea is the consortium is a 4-year program with the goal of collaboratively working on the primary technical issues of heavy-duty refueling stations identified and selected by the consortium members. So once the research topics are defined, we will evaluate and pursue the research and test the performance of the equipment, and the findings will be disseminated to the members to benefit their future facility build out. So the consortium offers a safe and non-customer facing test facility to evaluate the pressing needs of and to advance the technology. So as I said at the beginning of my talk, when it comes to hydrogen, our industry cannot afford to have accidents, and we should not gamble the untested technologies with customers. So here are some of the topics that we have preliminary identified and considering for the consortium. The program will be categorized into 3 broad groups: refueling equipment reliability, vehicle and HRS system integration, safety and environmental. We will be looking into various flow components, including gas compressors, cryogenic pumps, storage systems, valves, flow meters, pre-coolers, and IR communication, dispensers, hoses, and breakaways, and so on. The work can involve reliability, evaluation, standards, validation, fueling protocols, efficiency optimization, and safety evaluation. So while the consortium was developed from the heavy-duty automotive perspective, many of the ideas, I believe, are directly applicable for the aviation industry as well. So we welcome the opportunity to discuss and develop aviation-specific topics to be included in the consortium. And please reach out to me with your interests. And the last section of my talk is on the hydrogen safety and the standard tests. So the fire tech, we have fire tech department at SwRI, and it's one of the world's largest organizations dedicated to fire safety research and testing. We offer multidisciplinary fire and explosion testing research services, including fire resistance material, flammability and explosivity testing and standards tests and so on. So as you see in the video here, you know, again, hydrogen is associated with clean fuel, but it's very tricky fuel to handle due to its small molecule and flammability. And on the right is a video from the hydrogen garage test program we did back in 2010 down in our ballistic range. The slow motion video shows the ignition of a stoichiometric mixture of hydrogen and air. And you can see the roof goes flying and the garage door peels open. There is also an IR video of a lower concentration test where the flame front spreads across the roof and then back, reflecting the heat wave. Okay, so the compliance testing. So we perform multiple fuel tank tests and safety analysis each year, including compressed hydrogen storage systems. One of the tests that we can perform is bonfire testing with or without the PRD, flame impingement tests with cylinder only or mounted on in a vehicle, and in compliance with the GTR 13. FMVSS 307 and 308 for heavy duty vehicles were just recently published last month. So we are working on updating our tests to accommodate those requirements also. And here we're showing that our routinely performed burst tests also, cyclic pressure tests, environmental tests of storage tanks. Ballistic tests and at SwRI we can do either indoors or outdoors to perform gunfire tests, various calibers. I recently got a chance to really witness this on a Type 4 cylinder, and it was really interesting to see how easily the bullet can penetrate through the tank wall. And mechanical engineering department can run drop tests from 30 feet, or we can, there is a pendulum swing test as well. Drop test might be you know, of particular interest for some of you in the audience as you develop your drones or aerial vehicles. And lastly, our structural dynamics testing and evaluation offers product assurance with the thermal and humidity cycling, altitude testing up to 100,000 feet, and shock and vibration, impact, and tests and so on. So that concludes the test, but if I may, I would like to briefly touch upon one more thing, which was the H2ICE consortium. As you can see, this was one of the very recent consortium that we concluded. And then we are moving on to the second phase of this consortium, H2ICE 2 consortium. And again, I'm not going to be talking about in details, but we modified the Cummins CNG truck engine into hydrogen and integrated into this truck. And here is our product that we exhibited at the expo recently. And then you can see the program manager, Ryan Williams, talking in this video. So with that, thank you so much. I would like to end the presentation with a picture with our facility, liquid hydrogen facility, and the truck. And I would like to leave you with our contact information. So thank you so much for listening.
Fantastic presentation. I could have listened to that all day. Also, being on part of the blowing up of things looks like a really fun job. Thank you for that presentation. It was very informative. I'll start with the first question. I asked it in the chat, and you kind of answered it by saying that you welcome people from the aviation industry to be part of the consortium. My question is, It's, I guess, sort of a comment and a question. As I understand, the Toyota Mirai uses hydrogen. It's stored, I think, at like 700 bar in gaseous form. And it's heavy duty, like let's say trucking. Are they looking at using liquid hydrogen? And I'm wondering if aviation should be its own consortium, or if you think it fits into the heavy duty, simply because in aviation we have to deal with the FAA and we may have to be under stricter, regulation than automotive. What are your thoughts on that, I guess, is my question. You're muted.
Sure, yeah, if I may share my opinion, yes, we are aware of the liquid hydrogen storage design from Daimler, and Linde is pushing for some of the direct liquid hydrogen dispensing in Europe. And there are some initiatives here in the US as well. Some other companies are pursuing cryogenic compressed hydrogen. And so again, the design is still has not been really decided, and many are trying different methods, right? However, into your question about relevance to aviation, yes, it's possible, but it doesn't necessarily mean it is most efficient. And the reason being, it depends on your utilization. So, and I speak that from our painful experience with our liquid hydrogen facility also. So if your liquid hydrogen facility is not utilized continuously, you will see boil off. And boil offs meaning lost energy. Yeah, so you'll be losing a lot of, literally you're seeing money vaporizing into the air. And it's not necessarily what you may want to do. So it depends on your application and how frequently you use your vehicle.
So Danielle, this is Dennis. I don't know can you hear me okay?
I can hear you.
So to maybe add to that a little bit at a higher level, just thinking out loud, okay, maybe the aerospace and the heavy duty go together down a path for a little bit and then diverge, when it becomes right. But the technology is so new, there's probably common lessons learned that not one company should be trying to learn on their own. So maybe that's another format.
That's exactly what I was picturing. I think Denis, we share a brain sometimes because also I thought it was really funny that you had the bridge the gap slide. Denis has never seen that slide of mine, nor have I seen his. And that was my first time presenting that, so that was really funny. But yeah, go ahead.
And I don't know if you can see me now in video, but the bridge I have behind me is kind of ironic too.
Yeah, it is. So we'll open it up to questions now. If you have a question, go ahead and unmute. Let me see. I think the first question that I saw was from Angela, and then Denis, it looks like you answered that in the chat. Tom, Denis, I think you answered that as well, but Tom, if you want to ask your question to the group, that'd be great.
Yeah, I think I got part of my answer when he described the HD consortium. But I have a question basically in terms of operational use for refueling capacity. What needs you see in terms of sensing capabilities, sensors that can be used to monitor what goes on operationally with the refueling capacity? I'm thinking more in terms of, say, in an airport, in those situations. Do you have any conceptions as to what that might look like?
Yeah, can you repeat your question? Am I understanding correctly? You were asking about sensors.
Sensing capabilities for operational use for refueling facilities, say in an airport.
Sensors in the field in production.
Is it in the vehicle side or in the
refueling the refueling facility side, not the vehicle side?
Sensors, I think That's actually a good question, interesting question. And actually, that can be, potential topic for the consortium also. So like,
Mhm.
I've seen liquid hydrogen, especially the liquid hydrogen dispensing, it really huge nozzle that had to go attached to the vehicle, right? And with that, it was demonstrated as a manual hookup, but potentially, it can be done through some robotic kind of a automated system in future. And with that, that with sensor, sensor instrumentation, and maybe some safety, kind of additional safety built into it. So those kind of sensor based or even like a machine vision type based automation can be possible, but it really depends on where and how the industry wants to do, and we can work together in building those type of technologies. And for example, like again in the automotive, heavy duty automotive side, I'm seeing. Like here in the US, it's a single nozzle, but in Japan, for example, some of them are pursuing like a dual nozzle dispensing, and it has not been really settled. So it really, I can foresee a certain sensor base or additional, instrumentation required in the infrastructure side, for safety side as well. So. Yes, to answer your question, yes, I can see that.
Okay, thank you very much.
Thank you for the question.
Thanks. Next up, I see Michelle. Michelle, would you like to unmute and ask your question?
Do you mean me?
Sorry.
Yes. Okay, sorry.
Apologies.
Yeah.
Is it pronounced Michael?
Yeah, it's Michael. It's the
Okay.
Italian for Michael. Yes.
Okay, I apologize.
Of course, there was already an answer, but yeah, the reason for my question is that, of course, it's not easy to keep liquid hydrogen for a long time, especially due to boil off and the possible increase of pressure. Of course, if you are distributing the gas to the fuel cell testing, this is not a big problem. But if you need to keep the liquid hydrogen, that's maybe an issue, right?
I had answered that question with Richard.
Yeah.
It's refillable, basically, so.
I'm sorry, was there a question there? What was your question?
I think his question was
The original question was for how long you keep the liquid hydrogen in the tank.
How long?
Depends a lot on the
Yeah,
weather.
it depends on the your ambient temperature also, and also flow. It can depend on the flow rate also. What we noticed with our experience with our cryogenic pumps was that if the pump was operated at low flow rate, the pump can shut down and then turn back on and shut down, turn back on again. And in doing that repeated kind of a shutdown and on cycle, the cryogenic pump heats up and additional essentially liquid hydrogen had to be used to pre-cool that pump, and therefore wasting the efficiency or the fuel itself. So again, it depends on your condition, but again, in general, you want to maintain certain flow rate to be most efficient. And many of the companies are looking into liquid hydrogen supply, but again, and that is due to obviously with the gaseous compressed gas storage transport, it is very limiting in terms of the quantity. So that is the reason I believe many are looking into liquid hydrogen transport, and that is all right for the initial maybe the infrastructure build out. But in the long term, I do not see that as a feasible operation. Again, with compressed gas, you do not lose that. There is no ticking time, even in the refueling truck. But if should the vehicle break down during the transport, what would happen to that fuel? It's going to evaporate, right? And then also the other challenge is that unless there is a compressor either on site or cryogenic pump on site or built into the truck itself, the refueling process can take hours also, which is not necessarily too efficient again. So in the long term, I see maybe like a hydrogen pipeline could be the answer. Once you have a network of refueling stations, or from essentially a hydrogen production facilities built nearby, or maybe on-site generation through electrolyzer can be an option as well. But as of now, it depends on the electricity rate, and there are more research needed in the electrolyzer testing as well. The validation of the system and the CapEx need to come down also. So there are many improvements in research in that front as well.
We got a couple more questions in there.
Thank you for that. I will call on the next. I like to have people unmute and ask them. It builds people. You can see people's names and kind of get to know each other. Robert Viney or Vinny. I hope I'm saying. I've given it 2 guesses. I hope one of those are correct. Feel free to. Yes. Okay. You're up.
Okay, I was wondering if SwRI has any insights into the LD refueling station infrastructure in California, which doesn't seem to be highly successful yet, and whether any of the insights there might be helpful in applying to building a more successful HD truck hydrogen refueling network.
100%. Many of the lessons learned in the light duty side is directly applicable in the heavy duty side as well. What we found out, and again, I'm not necessarily the expert in this area, but what we found out was many of the issues were could be the communication error between the station, the dispenser, and the vehicle itself that caused the error, or even just the I don't know the term for that. There's essentially the simple transaction of that dispenser machine. And some I hear compressors could have failed if it was obviously it was a gaseous dispensing, so it needed to have the compressors, and that may have failed prematurely. So many of them are directly lessons learned from the light duty can be transferred to the heavy duty, and we should not be repeating those mistakes, right? So those are some of the obvious things we can do in designing the heavy duty refueling stations. Some of the companies that I am aware of are directly going with the cryogenic pump compression and then vaporizing at 700 bar pressure. So bypassing the compressor and directly refueling with the thermal management. So that is an interesting development, and we will see what becomes kind of the champion of the technology. However, again, many of these companies taking the risks in testing their untested, unproven technologies at the customer-facing facilities, refueling stations, and we should be very careful with that.
So is your consortium looking at the learning? Is it compiling the learnings from the LD
No,
station?
that would be, yeah, so that would be one of them, but you know, obviously the entire point is to really, once we identify, actually, once the industry gives us their feedback and tell us what they want to, what you want to test, we will get to those research and then share that collaboratively again, or share that information back to you. So you know, if you try to take on that task on your own, it could be very costly. But the idea is to share that resources, pull the resources, essentially money, to be tested at SwRI's facility, and then get the same results at a fraction of the cost.
Okay, great. Thank you.
To that point, Richard, that was it's so similar to HYSKY. You know, our goal was to bring the hydrogen aviation community together for exactly that reason as well, because we were all sharing the same problems. Is there a fee to join the consortium? What does that look like? How, because what I'm thinking is, you know, HYSKY could collectively gather the challenges of the aviation industry, and you know, without every single person, I mean, you could join, but what does that look like to be part of that?
Yeah, so there will be annual fees depending on the tiers. So we have created several different tiers, like, you know, OEM, the operators, suppliers, and so on. But I guess, you know, we can definitely, if you're interested in more like a collective or group kind of a tier, we can discuss that offline and see how that maybe arranged.
Yeah, Danielle, all of them are a little bit different. So it's a case by case basis, and generally they run for about 3 years. It's like a 3-year type of commitment. So there's a lot of variables to it that we could talk about individually.
Yeah, so kind of similar to what you just suggested, you know, I'm hearing many of the hydrogen hubs have plans to introduce like, you know, thousands of heavy duty vehicles, right? But many of them are doing independently. Essentially, their members are trying to build their own vehicles, not necessarily build the vehicles, but to build the infrastructure, maybe to contract out to some companies. But you know, again, you should not be on your own, and again, you should not be making the same mistakes, right? So the point is to reduce those risks, de-risks those, you know, some of the issues you will be facing through the consortium, and again, pooling the resources to do so more affordably.
And hopefully, especially on the aviation side, that would kind of help drive some regulations and stuff. If everybody was kind of working together and saying, hey, this is what we're doing, it may, you know, help drive that along, which obviously is needed.
Yeah, I agree. Definitely an opportunity here and another conversation we'll have offline. Thank you for that. Okay, next, Daniel, you're up. This is a very interesting question. I'm anxious for the answer to this. I'm not even going to attempt to pronounce your last name, but starts with an M. So Daniel M, if you're on, please ask.
Hi.
Okay, thank you. I think I've tried to say that before, and I think I butchered it.
Well, I just have some comments. Working with Lindy for 12 years when I was younger, while going to engineering school, I learned a lot about liquid hydrogen. And one of the issues, you know, if you start looking recently, is the cost of transporting liquid hydrogen is somewhere between $1.25 to $1.35 a kilogram, up to 225 kilometers. I've been spending last several years looking at alternatives and been on the phone with the military, very high level people who run bases, and they are getting away from liquid hydrogen totally. To use a quote from one of the generals, we don't want some nutcase with an RPG blowing up our facility. So I was told at that particular time that if I'm smart, I need to focus on hydrogen carriers. So I did. I looked at a whole bunch of different things. And after about a year and a half, I can tell you that the methanol, the hydrogen is a much better way to go. And the reason is that we have access to technology now that can take the methanol and convert it directly to hydrogen on the spot. So all the issues and problems and concerns that everybody's fighting over with this liquid hydrogen is gone. One of the other issues is transportation. While at Lindy, I remember there were certain trestles and bridges and other underpasses we could not go under by law due to safety issues, and that's all gone with using methanol. So anyway, I just wanted to bring up to the team that based on all the calculations and the work I've been doing, you guys should just consider the methanol, biomethanol made from cellulosic or some green source as a better way to to move it. One of the other things I talked about is storing the hydrogen. You'll see right down my message after it. One of the things I saw that was very, very interesting was a demonstration of taking 2 tube trailers full of hydrogen about 25 years ago and taking them down an airport that was closed, a runway. And halfway down, they would disconnect the trailer at about 10, 15 miles an hour and let the trailer slide into if you can imagine, a stainless steel cutting blade that was in the air into the cement. So when that trailer hit the blade, it would split it open slightly. And as you can imagine, there was a little flame there, a torch, and it would be a gigantic whoosh, which you could feel on your chest. Subsequently, they bought back the next tube trailer that was filled with the hydrogen the same way, but there was one big difference. It was filled with carbon nanotubes. And when they did the exact same thing, they released the trailer and let it hit that and cut it open. There was just a very, very small leakage of the hydrogen coming out of the trailer. We then bought over a small little truck with a little generator hooked up to 2 electrodes and put the power onto it, and whoosh, it came out. So in my opinion, based on what I saw, carbon nanotubes appear to be an alternate way of storing more safely gaseous hydrogen. So anyway, I just wanted to bring up those points for thought.
Yeah, very interesting, and thank you so much for sharing that. I think I'd like to learn more about that technology myself. So I cannot comment on it because I don't know. However, you're correct that there are many companies looking into different methods. Methanol is one of them. Toluene is another. Or even like metal hydride is potential. But the question is, it's especially in the end, the question is going to be, what's going to be the round trip efficiency. So, as you starting from the original source of the energy, and then how much energy was putting in, and then maybe to produce hydrogen first, right? And then you have to store it or convert it into some other form of chemical energy or maybe some solid state materials, and then transport it. You typically have to put in energy again, heat or something else to convert it back to hydrogen. So you have to look at it holistically and look at the whole round trip efficiency. So and obviously the safety factor and everything else needs to be considered. So I think that nanotube technology you just mentioned seems very promising, but we would like to look at it and consider that for the potential transport side of the equation.
Thank you.
Yeah, thanks for those comments, Daniel. I think I would love to have you present on HYSKY Monthly on that, what you saw. That was super interesting. I also just want to mention that Element 1, they're looking at methanol and we have their CEO, Dave Edlin, was one of our past speakers. So again, on our YouTube channel, you can go back and watch that. They talk in depth about methanol. I think methanol, it could be ethanol. I get the two mixed
No,
up.
it was methanol. Yeah.
It was methanol, thank you. And then they spun out E1 Air. So take a look at that video from a couple of years ago. It's on our YouTube. And then you can look at E1 Air and see kind of what they're working on. Who are you with now, Daniel?
I'm with a group called Syntex NRG, and we're looking at putting various projects here in Europe. And it's just like I said, I've been doing a lot of research very deep for the last 2 years, and I just see a real possibility and a real potential.
Would love to
Daniel?
chat more. Yep.
Can we pick up the question about the boil off capture?
Yep. Nico. Yep. Nico, do you want to come on and ask your question?
Sure. Can you hear me?
Yep.
So Nico Bauken with GTI Energy, and I've been working in this space for a while, and also specifically related to mobility and fueling stations. What I don't think I heard it, but I was wondering what your capabilities are to assess boil off capture and use systems, because it keeps coming up in whatever discussion you have when it's related to liquid hydrogen, whether it's at a station or on board of a vehicle, especially in this context of aviation. What can you contribute, or what capabilities do you have to contribute to deal with that boil off? Because obviously the hydrogen is not always in use. You touched on a previous question about what does it look like, how long can you keep your liquid hydrogen in your tank? Would be nice to hear a little bit more about that, to get a sense of how we could approach you with this topic in the future. Thank you.
Okay, thank you so much for the question, Nico. That's a little bit of a tough question for me to answer. But
That's why I gave it to you.
Oh, okay. Thank you, Dennis. Again, we have experienced the boil offs with our facility here at SwRI also, and that is actually kind of an ongoing battle sometimes. But there are ways to potentially capture the boil off the hydrogen. But again, it comes with additional infrastructure equipment, essentially, right? Equipment investment or additional energy usage. So I am aware that some companies like a Gen H2, I believe, are working on the reliquefaction system, and I think we did talk to them as well as looked into their incorporating that into our facility as well. But the flow rate for our application, we were looking for the potential liquid hydrogen, the cycling test of the dispensing. So with that, the flow rate was not sufficient for us. And again, with very high CapEx side of it, that was not, I believe, something we were going to do at the time. But definitely I am aware of those technologies out there. But again, I'm not necessarily a subject matter expert on that side of it, so I'll limit my comment to that.
Okay, thank you. And really, I'm asking because that's the answer of also commercial entities. They don't really want to. It's costly to do that, and because you're a research entity, I was just wondering what your capabilities were to assess systems like that. And obviously, yeah, that comes at a cost. But if others pay for it, do you have capabilities to assess? Because the commercial entities that run fueling stations, they don't want to do it because it adds cost to their setup and complexity, and they really should focus on getting the fuel out instead of that part of the system. Okay, thank you.
Yeah, I got you now. So if you're asking about our testing capabilities, and I think yes, the answer is that is within our capability. But I'll have to connect you to the right group. who can run that. And if you reach out to me by email, I'll be more than happy to connect you to that mechanical engineering department that we have.
Okay, thank you.
Thanks so much. Okay, last but not least, Will, your hand is up. I see it. And if we have time, Jay, you'll go next. But Will, you take it away.
Hi, thanks everybody. Thanks, Danielle. And nice to be here. I'm with Tuverity, which is one of the sponsors, and we're happy to be a sponsor. We've got a lot of value out of it. So what we do is we use ethanol as a liquid organic hydrogen carrier. So there's no round trip. We just buy ethanol on the open market, which is available everywhere, because it's 10% of our gasoline in every state. So it's a very inexpensive way. We have a thermocatalytic process, very compact. And Daniel, I want to mention a couple of things that I don't know if you're in touch with the first public hydrogen utility that was established in California in January. And we were chosen as a prime supplier for them of hydrogen using our systems. We were actually chosen because we are going to supply hydrogen to 17 transit districts in California. They're going to buy 1,000 buses, 1,000 hydrogen buses. And in addition, we're speaking with the Fresno airport, and we are in negotiations with at least 3 or 4 companies that are making hydrogen engines for planes, or they're making the whole hydrogen plane. I'm sorry, Daniel, I can't on this call. I can't reveal who they are.
It's
But
okay.
one
Well, I just want to let you know we are at the top of the hour, and I want to
Yes,
be very
okay.
respectful of our guest speaker's time.
Yeah.
So
One
wrap it
thing-
up quickly, please.
Yeah. So one thing that I wanted to mention, I wanted to ask you if you have ever heard of Jet Zero.
No.
Okay.
I'm sorry.
All of you need to take a look at Jet Zero. They've recently hired a lot of the Airbus engineers to bring them over. They own a large building right on the Long Beach airport.
Okay,
like next to the runway.
We're gonna look them up,
Yeah.
and we also are very
Okay.
grateful for your sponsorship, and huge thanks to SwRI. Now I know how to say it, so I've been saying it wrong this entire time. But thank you so much to all of you. Thank you so much, Dennis and Richard. If you didn't capture the email me and I can introduce you all. But again, another fantastic episode of HYSKY Monthly. Thanks so much to our speakers and guests. Everybody have a wonderful week.
Thanks for the opportunity, Danielle. Bye-bye.
You bet. Bye.
Bye.
Thanks.